Mwalimu Theophil Academy reminds you that success is not an overnight process, but consistency. Welcome for today's session.
In this lesson, you are going to learn about Faraday's first law of electrolysis. Faraday's first law of electrolysis states that the mass of a substance liberated at or absorbed from an electrode during electrolysis is directly proportional to the quantity of electricity passed through the electrolyte. Now, according to this law, you can see that the mass liberated is directly proportional to the mass liberated is directly proportional to the quantity of electricity. As you can see here, I have written that the mass is directly proportional to current times time. You have to know that when you take current times time, it is where we get the quantity of electricity, the charge. Now, after removing the proportionality sign, we get mass is equal to ZIT. What is the value of Z? Z is the constant value known as electrochemical equivalent. Now, this is a standard formula used to refer the Faraday's first law of electrolysis. And from this formula, it means that M stands for mass of a substance discharged, Z stands for electrochemical equivalent of a substance to be discharged, I is the amount of electric current passed through the electrolyte, T is the time taken during electrolysis. Now, from all of these parameters, we have seen one known as electrochemical equivalent of a substance. What is electrochemical equivalent of a substance? Simply we say that the electrochemical equivalent, which is denoted as Z of a substance, is the mass of the substance discharged when 1 coulomb of electricity is passed through an electrolyte. So, whenever you're told about an electrochemical equivalent of a substance, you have to take note that it is the mass of a substance discharged during electrolysis when 1 coulomb of electricity is passed through an electrolyte. Now, after this definition of electrochemical equivalent, let us see its unit. Electrochemical equivalent is expressed as gram per coulomb. As we've said that it is the mass liberated when 1 coulomb of electricity is passed through an electrolyte. Note, electrochemical equivalent of a substance is given by the formula. Electrochemical equivalent is calculated by using this formula. It is the relative atomic mass over valence of an element concerned times Faraday's constant. What are these stands for? Let us see. Z in this formula stands for electrochemical equivalent of a substance as usual, as we have seen in the previous explanation. RAM stands for relative atomic mass of a substance whose ion is discharged. V stands for the valence of an element whose ion is discharged. And F stands for Faraday's constant. And this Faraday's constant is equal to 96,500 coulombs, as you can see. So, whenever you're asked to calculate the electrochemical equivalent of a substance, you have to take note that it is the relative atomic mass over the product of valence and Faraday's constant. Now, we have introduced a new term, which is Faraday's constant. What is Faraday's constant? Simply we say that Faraday's constant is the amount of electric charge carried by 1 mole of electrons. So, the amount of electric charge carried by 1 mole of an electron is what we call the Faraday's constant. You have to note that 1 Faraday is the quantity of electric charge carried by 1 mole of electrons. That is to say, 1 mole of electron is equivalent to 1 Faraday and is equal to 96,500 coulombs. You have to note this relation, that 1 mole of electron is equivalent to 1 Faraday, and 1 Faraday is equal to 96,500 coulombs. So, after this, let us see the way we can calculate different electrochemical equivalents of various elements. here we are required to calculate the electrochemical equivalent of copper. As we have said that the electrochemical equivalent is equal to the relative atomic mass of the element of the product of valence and the Faraday's constant. Now, for the copper, it is known that the relative atomic mass of 1 mole of copper is 63.5 grams. So this is divided by the product of its valence and Faraday's constant. The valence of copper is 2 times Faraday's constant, which is 96,500 Coulombs. As we have said that 1 Faraday is equal to 96,500 Coulombs. So here, what are we going to get? Now let us compute it by using a calculator. It is 63.5 over 2 times 96,500. You get 3. The answer is equal to 3.290 times 10 raised to -4. This is gram per coulomb. Gram per coulomb. As we have said that the unit for electrochemical equivalent is gram per coulomb, as I have written there. Now this is the electrochemical equivalent of copper. This is the electrochemical equivalent of copper. Let us see the electrochemical equivalent for oxygen. For oxygen here, the relative atomic mass of oxygen is 16. So we take 16 over its valence. The valence of oxygen is 2 times Faraday's constant, which is 96,500 Coulomb. So here, when we compute in a calculator, we can compute it as follows: 16 over bracket 2 times 96,500. 500. The answer is 8.290 times 10 raised to -5 gram per coulomb. This is the electrochemical equivalent for oxygen. So whenever you are asked to find the electrochemical equivalent of oxygen, you have to know that it is 8.290 times 10 raised to -5 gram per coulomb. So this is the way we can find the electrochemical equivalent of any element concerned. Let us start solving various examples concerning with Faraday's first law of electrolysis. Example 1. How long should a current of 5 ampere be passed through a solution of silver chloride in order to deposit 3.24 kg of silver metal at the cathode? You are given electrochemical equivalent of silver is 1.118 times 10 raised to -3 gram per coulomb. Now, let us see the way we may solve this question. Here, let us start with a solution. After writing the solution, let us analyze the data which we have. Data given. In this question, we are given the current. We are given current electricity I, which is equal to 5 ampere. Also, apart from current, we are given the mass of silver deposited. It was mass of silver deposited. M is equal to 3.24 kilogram. Also, we are given electrochemical equivalent of silver. Electrochemical equivalent of silver. Electrochemical equivalent of silver. And you have to know that electrochemical equivalent is is Z of silver is equal to, we are given 1.118 times 10 raised to negative 3 gram per coulomb. These are the data we have. And what is asked here? We are asked to find the time, as the question asks, how long should the current of 5 ampere be passed through a solution of silver chloride in order to deposit 3.24 kilogram of silver metal at the cathode. Now, how long will that time is required? Time is required. Time T we are not given. So we are required to find the time for this mass of 3.24 to be deposited when the current of 5 ampere will be passed through an electrolyte of silver chloride. Now, let us see the way. Here, according to Faraday's first law of electrolysis, we are told that mass of silver deposited is equal to electrochemical equivalent times current times time. This is according to Faraday's first law, that the mass liberated at or dissolved from the electrode is that proportion to the quantity of electric current passing through the particular electrolyte. Now, after there, here what we are looking for is the time. If it is the time, it means that to get time from this equation will be equal to mass over electrochemical equivalent times current. But you have to remember that here the given electrochemical equivalent is in gram per coulomb. So even this mass as it is in kilogram, so to make them as this mass is in kilogram, it should be changed into gram so as to match with a given electrochemical equivalent. Now, for the case of mass, we are going to multiply this 3.24 kilogram times 1000 so as to make it to be in gram. So here we are going to substitute these values. In terms of mass, we are going to put 3.24 times 1000. When we multiply by 1000, we change the kilogram into gram. Here, let us divide by electrochemical equivalent 1.118 times 10 raised to negative 3 times this is electrochemical equivalent times electric current, which is 5 ampere. Now, let us divide. Let us use a calculator to compute this mathematical term. We have 3.24 times 1000 over 1.118 times 10 raised to negative 3 times 5. Here the answer we get is 5.7961 times 10 raised to 5. You have to remember this is time, so it is in second. So this is the answer. When we approximate it, we get almost 5.8 times 10 raised to 5 seconds. Now, it will take 5.8 times 10 raised to 5 seconds for the mass of 3.24 of silver to be deposited at cathode. Now, this is the required time for it to be deposited. Apart from using the formula directly obtained from the Faraday's first law of electrolysis, we have also an alternative for this question. Let us see an alternative. So we say alternatively, we may solve it as follows. Alternative. The alternative method which we use here is to use a balanced chemical equation. As we know, the electrolysis of silver chloride at the cathode, it means that silver ion will be deposited. Now, if silver ion is going to be discharged, it means that it is going to be reduced. Now, silver ion is going to be reduced at cathode and it becomes silver metal. Let us see its equation. Reaction at cathode. Reaction at cathode. It means that silver ion is going to be reduced. It means that it will regain the lost electrons and it becomes a silver metal, which is in solid form. Here it is in aqueous. So this is a balanced chemical equation for the reaction at cathode, whereby silver ion is going to be reduced, as you may see. Now, from this balanced chemical equation, we can use the mole concept to get the relation between the used moles of electrons and the deposited amount of silver. Now we say that from this equation that one mole of electrons is equivalent to 1 mole of silver metal. As you can see, it means that when 1 mole of electrons is used, the 1 mole of silver solid is deposited. Now let us see from this relation, we may also compare it. If you remember, 1 mole of electrons is equivalent to 1 Faraday. Now, if 1 mole of electrons is equivalent to 1 Faraday, it means that instead of writing 1 mole of electrons, I can write 1 Faraday. Now it means that 1 Faraday is equivalent to 1 mole of silver metal. Also, when I say Faraday, 1 Faraday, you have to remember, is equal to 96,500 coulombs. Now, I can change this Faradays into coulombs. I mean, the quantity of electricity in terms of charge. So here, it is 1 Faradays, it means that it is 1 times 96, it is 1 times 96,500 coulombs. Will be equivalent to 1 mole of silver. But also, you have to remember that 1 mole of silver is equal to 180 grams. So, instead of writing 1 mole of silver, I am going to write 180 grams of silver. Why have I changed it to mass? I have changed it to mass so as to compare with the given amount, which is in terms of mass. Now, let us see the way we do. So, 1 times 96,500 coulombs is equivalent to 180 grams of silver. Now, you may ask, let us use the data from the question. Here, it means that we are given 3.24. These are in terms of kilograms. So to change it into gram, we multiply by 1,000 to make it into gram. Now, this is the amount deposited at cathode, will be equivalent to how much coulombs. Here, we are required to convert the given current to relate the given current and time so as to make them to be in coulombs. So to get the coulombs from the question we are given, it means that we are going to take the current times time. It will be 5 times t, as t is to be calculated. T is not known. So when you take the 5 ampere we are given times the time taken, it means that we are going to get the charge in terms of coulomb, which will match with this one from the standard balanced equation. Now, after there, what is required? We are looking for t. To get t here, let us cross multiplication. When we cross multiplication, we can be in the position of obtaining a known value of t, which is asked in our question there. 5t will be multiplied with the 108. So it will be 5t times 108. It will be equal to, also, 1 times 9600 will be multiplied by 3.24 times 1000, as you see. Here we are going to get the values. Let us start by multiplying 5 and 108. 5 times 108. We are going to get 540 t. As t is not known, you have to remember it with the time. Now we are looking for t. It will be equal to, let us multiply also this. Here is 1 times 96,500 times 3.24 times 1,000. Here we are going to have 312,660,000. Now, what next is to divide by 540 both sides so as to obtain a known value of t, which is our required time. Now, it will be 540 t is equal to 312,660,000. We divide by 540 both sides. 540 both sides. Now we are going to get t. What is the value of t? T will be equal to, let us divide. Now on this side we are going to cancel out 540 are going to cancel out. Here we are going to remain with the t. Now our t will be equal to 312,660,000 over 540. You have to know the answer obtained here will be in terms of seconds, as we are looking for time. Now let us divide that value. We have 1,312,660,123 over 540. Here the answer which you get is 5.79 times 10 raised to 5 times 10 raised to 5 seconds. When you approximate this, you get 5.8 times 10 raised to 5 seconds. Now you can find that the answers are the same. The answer which you obtained in the first approach is the same as when we used the balanced chemical equation. Now, this is the way we carry out the calculations concerning with the Faraday's first law of electrolysis. So here we say that the current it will take 5.8 times 10 raised to 5 seconds for 3.24 kilogram of silver to be deposited at cathode. This is the answer which is required for this question. Now, I hope you have gained a lot. On the way, we solve various problems concerning with the Faraday's first law of electrolysis. The second example states that a current of 3.2 ampere is passed through a solution of copper 2 sulfate for 30 minutes. What is the mass of copper deposited at a cathode? You are given the relative atomic mass of copper is 63.5. The relative atomic mass of sulfur is 32. The relative atomic mass of oxygen is 16. Solution. Let us first of all analyze the data which we have. Data given. The data given here, we are given current electricity, current I. The current you are given here is 3.2 ampere. 3.2 ampere. Another data which we have time, 30 minutes. Time. We are given time. Time T is equal to 30 minutes. 30 minutes. When you convert this time into seconds, you are going to have 30 times 60, which will be seconds. Now this will be equal to 1,000 800 seconds. This is the time which is equivalent to 30 minutes. 1800 seconds. Now, another data we have here, we have almost relative atomic masses of these various elements: copper, sulfur, and oxygen. Now, what is required here is to calculate the mass of copper deposited. The mass M of copper deposited. Mass M of copper deposited is required. It's not known. And now let us use this data. Now let us use this data to calculate this mass of copper deposited on the cathode. Which approach are you going to use? Here we may use the approach of firstly balancing the chemical equation. I mean that by considering the reaction which was occurring at cathode. As you know, at cathode, copper is going to be reduced. Now, copper will be reduced to copper atom. I have decided to use this of balanced chemical equation because we are not given the electrochemical equivalent of copper directly. So, we may use these prevailing data directly without involvement of electrochemical equivalent by using the balanced chemical equation. Now let us balance it. Here, let us consider reaction at cathode. The reaction at cathode will involve the reduction of copper ion into copper metal. Now it will be copper 2 ion. It will gain the electrons equivalent to these ions, I mean 2 electrons, and it will be discharged to copper, which is solid. Now this is in aqueous form. As you can see, this is the balanced equation for this reaction. Now we use the concept of mole concept, especially on the section of stoichiometry. Here, 2 moles of electrons are equivalent with 1 mole of copper solid. So 2 moles of electrons, we say 2 moles of electrons are equivalent to 1 mole of copper metal. Here, these 2 moles of electrons, if you remember, we said that the number of moles of electrons are equivalent to the number of Faradays. So instead of writing 2 moles of electrons, we can also write 2 Faradays. Now we say 2 Faradays are equivalent to 1 mole of copper. So if this is the case, here we are going to convert these Faradays into Coulombs so as to be in the position of being able of using the given current and time. As you know, when we take current times time, we get that charge in terms of coulombs. So in order to make it to relate with the standard equation here which we are preparing, let us convert these Faradays into coulombs. You have to know that 1 Faraday is equal to 96,500 coulombs. So here, to convert these 2 Faradays into coulombs, it will be 2 times 96,500 coulombs. So instead of writing 2 Faradays, I can write 2 times 96,500 coulombs. Now 2 times 96,500 coulombs will be equivalent to 1 mole of copper. But also, I am going to convert this 1 mole of copper into mass, as you have to know that what we are looking here, we are required to calculate the mass of copper deposited at cathode. So if we are required to calculate the mass of copper deposited at cathode, it means that even this mole can be compared with the equivalent mass, so as to be in the position of relating the mass obtained with the particular mass which is asked. So here, 1 mole of copper, we are told that 1 mole of copper is equal to 63.5 gram per mole. Now, it is, instead of writing 1 mole, I'm going to write 63.5 gram of copper. So this is the way. Here, this is the data from the standard equation. This is the data from the standard equation. Now from this, let us compare it with the data from the given, let us compare it with the data from the question. From the question, we are given the current of 3.2 ampere in time of 1,800 seconds. So, as I've told you that when we take the product of current and time, we get the charge in terms of Coulomb as we have here. So it means this 3.2 ampere times 3.2 ampere times 1,008 seconds will be equivalent to how much mass, to m, as the mass which is required is not known. So here, this current, when this current is applied within this time, 1,080 seconds, we are going to get the mass m. Mass m of copper will be deposited at the cathode, but this mass is not known and is what we are looking for according to the question given. Now, to get this mass, let us cross multiplication. We are going to cross multiplication of these values which we have. After crossing multiplication, here we are going to have 2 times 96,500 coulombs times m this. This answer will be equal to 3.2 times 1,800 times 63.5. Now here, let us use a calculator to multiply these various values. Now we have on the left hand side you have 2 times 96,500. When you multiply it, you get 193,000. This is m. As we have seen, we've got 193,000 m. As you know that m is not known. Now this value will be equal to 3.2 times 1,800 times 63.5. When you multiply this, you get 365,760. Now this is the answer we get on the right hand side. Now after obtaining this, what is next is to divide by 193,000 both sides so as to remain with the m. Now how it comes, it will be this way: 193,000 m is equal to 760. So here we are in the position of dividing by 193,000 both sides so as to remain with the m. 193,000 both sides. We divide by 193 both sides so as to remain with the value of m. Now this value will cancel out because they are equal. So on the left hand side we are going to remain with the m. Now our m will be equal to, let us take this over this. Here we are going to have this of 193,000. The answer here becomes 1.895. This is the answer. Now you have to remember this is mass, so it is in a gram. As all data is the forms of mass, they are in a gram. So even the final answer will be the mass which is in a gram. Here, when you approximate this value, you're going to have 1.90 gram. So this is the mass of copper which will be deposited at the cathode. Apart from this approach, also we have an alternative. We have an alternative. The alternative which can be used here, the alternative, apart from this, let us have an alternative. Alternatively, an alternative which can be used to solve this question is to use directly the formula from Faraday's first law of electrolysis. But you have to know that I told you before, I told you when I started solving this, that in this question, what lacking is the electrochemical equivalent. So here, we may start finding the electrochemical equivalent of copper. After getting the electrochemical equivalent, we will be in the position of using the formula from Faraday's first law directly without any problem. Now, let us first of all finding the electrochemical equivalent, the electrochemical equivalent of copper, equivalent of copper. Now, I think you remember, we have said that to get the electrochemical equivalent is equal to relative atomic mass over the product of valence and the Faraday's constant. I think you remember. Now let us see now what element are we dealing with? We are dealing with the copper. Now, the relative atomic mass of copper is how much? We are given that it is 63.5. Now, if it is 63.5, it must put in the part of numerator 63.5 over. We are going to divide with the valence of copper. Copper is a valence of 2. So we put 2 here times Faraday's constant. Faraday's constant is equal to 96,500 coulombs. So it is 96,500. Here, now let us divide so as to get the electrochemical equivalent of copper. Let us use a calculator to compute that mathematical term. We have 63.5 over 2 times 96,500. The answer which we get here is 3.290 times 10 raised to negative 4. 10 raised to negative 4. This is the electrochemical equivalent of copper. Now, what is the unit? I told you that the unit for electrochemical equivalent is gram per coulomb. So, the electrochemical equivalent of copper is 3.290 times 10 raised to negative 4 gram per coulomb. Now, after that, let us solve directly by using the equation obtained when the Faraday's first law of electrolysis is applied. The equation is that we are told that to get mass from Faraday's first law of electrolysis, mass is direct proportion to the quantity of electricity passed through the electrolyte. Now, mass is equal to Z, which is electrochemical equivalent, times current times time. This is the equation according to Faraday's first law of electrolysis. Now, let us substitute the value of Z, I, and T so as to get the mass. Here, we have obtained that the electrochemical equivalent of copper is 3.290 times 10 raised to negative 4. 10 raised to negative 4 times current. Current we are given is 3.2 ampere times time. Time we are given is 30 minutes, which is equivalent to 1,800 seconds. 1,800 seconds. Now, what do we get? Let us compute in a calculator. We have 3.2 times 3.290 times 10 raised to negative 4 times 3.2 times 1,800. What do we get? We get 1.89504. This you have to know is in terms of grams. So this can be approximated as 1.90 gram of copper. So you can find that the values obtained in the alternative and in the first solution we have made are equal. So we say that, we conclude by saying that the mass of copper deposited at the cathode will be 1.90 gram. Yes, that is the way we carry out various calculations concerning with the Faraday's first law of electrolysis. I hope you have understood well the way we use the two methods, the two ways of calculating various problems concerning with the Faraday's first law of electrolysis. One technique we use is to use a balanced chemical equation, and the second is to use direct formula from Faraday's first law of electrolysis. Now this was the second example. Let us see a third example. Example 3 states that calculate the mass of magnesium metal that will be produced during electrolysis of molten magnesium chloride if a current of 1.93 ampere is passed through for 16 minutes and 40 seconds. You are also given the relative atomic mass of magnesium is 24 and of chlorine is 35.5. Now, let us see the solution for this question. Here, let us first analyze the data which we have. Now, solution. Data given. The data given here, we are given the current, electrical current I, we are given that it is 1.93 ampere. Another data we are given is time T. Time T we are given is, 60 minutes and 40 seconds. So this is 16 minutes and 40 seconds. When you convert the minutes into seconds, you're going to have 16 minutes times 60. Now this will be in 2 seconds, and the answer obtained is going to be added with 40. It's going to be added to 40. Those, all of them will be in terms of seconds. When you multiply this, you're going to get 960 plus 40. This will be equal to 1000 seconds. 1000 seconds. So this is the given time. Also, we are given the relative atomic masses of magnesium and chlorine. So what is required here to calculate the mass of magnesium deposited, magnesium metal? Mass M of magnesium. Mass M of magnesium deposited on cathode. Deposited at cathode. Is equal to how much? So the task is to find the mass which will be deposited when the current of 1.93 ampere is passed through that electrolyte within 1000 seconds. Now, to calculate this by using directly the data given, let us use the balanced chemical equation, which shows the reduction of magnesium ion into magnesium metal. Now, there is this reaction at cathode. Reaction at cathode will be the magnesium ion. Magnesium ion is going to be reduced by gaining 2 electrons and becomes magnesium metal. As you see it here, it becomes magnesium metal. So from this balanced chemical equation, we can use the idea of mole concept and stoichiometry so as to know the mass of magnesium which will be deposited. Now, from this equation, 2 moles of electrons are required so as to deposit 1 more of magnesium. 1 more of magnesium. Now, this is the details from the standard balanced chemical equation. So from these details, now let us relate them with the given data. The given data, we have time and current. So time and current are enough to give us the electric charge in terms of coulombs. So if they give us the electric charge in terms of coulombs, let us even the data we have from the standard equation be changed in that direction. So here we are going to convert these 2 moles of electrons into charge. So here we say that 2 moles of electrons are equivalent to 2 Faradays. This is true, that the number of moles are equivalent to the number of Faradays. So instead of writing 2 moles of electrons, I'm going to write 2 Faradays. Also, you have to know 1 mole of magnesium is equivalent to 24 gram per mole. I can say 24 gram. So you have also to know that 1 mole of magnesium is equivalent to 24 gram. Oh, now in place of 1 mole of magnesium, I'm going to put 24 gram, and in place of 2 moles of electrons, I'm going to put 2 Faradays. So here, why I have started changing these into Faradays and gram? This is to match with the data which we have. In the question, we are asking to find the mass. So these given moles of magnesium should be changed into mass so as to simplify the road for us to get the required mass. Also, I've changed the electrons into Faradays, as the Faradays are going finally to be changed into charge, I mean in form of coulombs. So here, instead of writing this, I can use this data, so it will be 2 Faradays are equivalent. 2 Faradays are equivalent to 24 gram of magnesium. It becomes this way. Now, what is next? Here, let us change the Faradays into coulombs, I mean to charge. It will be 1 Faraday is equal to 96,500 coulombs. So instead of writing Faradays, I am putting 2 times 96,500 coulombs. So 2 times 96,500 coulombs is equal to 2 Faradays. Now this will be equal to equivalent to 24 gram of magnesium. 24 gram of magnesium. After that, now we are in the position of being able to compare this equation with the given data. Now, in the left-hand side, you have coulombs, and as we are given time and current, we can change this into coulombs, to charge. As you know, to get charge is equal to current times time. So it means that when I take 1.93 ampere times 1,000 seconds. 1,000 seconds. These are equivalent to the mass which will be produced and which is not known as it is asked in the question. So will be equivalent to M, mass of magnesium, which is to be calculated. As this mass will depend on the current applied within a given time. So here, how are we going to get this mass of magnesium? How are we going to get this mass of magnesium? We are going to get it by crossing multiplication. We are going to get it by crossing multiplication. By crossing multiplication, we are going to get 2 times 96,500 times M. This mass is equal to this value times this. So it will be 1.93 times 1,000 times 24. It will be this way. It will look this way. Now, how can I get mass? Let us first multiply the values which are on each side. Here we have, on the left hand side, we have 2 times 96,500 Here it brings 193,000 m, as m is not known, is equal to 1.93 times 1000 times 24. Here you get 46,320. So what next year? What next year is to get the value of m. So to obtain the value of m, you're going to divide by 193,000 both sides. So here we have 193,000 m is equal to 46,320. So you divide by 193 both sides. 193,000 both sides. Here we're going to remain with the m. So the value of m will be equal to 46,320 over 193,000. You have to know that this is mass, so it will be in gram. It will be in gram. Let us now divide. Now let us divide. We are going to divide 46,320 over 193,000. What do we get? The answer here becomes 0.24. Becomes 0.24 gram. So this is the mass of magnesium which will be deposited at cathode. This is the mass of magnesium to be deposited at cathode. Apart from using this, we may use an alternative. Alternatively, we say that alternatively we may use the formula according to Faraday's first law of electrolysis. That the formula say that mass is equal to ZIT. It means that mass deposited is equal to electrochemical equivalent times current times time. In this equation, to get this mass, you must have these all three data, but we are only having two. We have current and time, and we are not given the electrochemical equivalent of magnesium. To calculate the electrochemical equivalent, to calculate Z, I told you that, well, we are told that to calculate the electrochemical equivalent of any element is equal to relative atomic mass over valence times Faraday's constant. So for magnesium, if we are looking for magnesium, the value of electrochemical equivalent will be equal to its relative atomic mass. The relative atomic mass of magnesium is 24 gram. Now you take 24, you divide by its valence. The valence of magnesium is 2 times the Faraday's constant is 96,500. After getting this electrochemical equivalent of magnesium, now we are able to compute it in this formula so as to get mass. Now we get our mass will be equal to electrochemical equivalent, which is 24 over 2 times 96, 2 times 96,500. 96,500. After there, this is electrochemical equivalent, which is indicated as I said. We multiply with current. What current do we have? The current we are given is 1.3. The current we have is 1.93 ampere times the time given. The time given here is 1,000 seconds. 1,000 seconds. So here the answer obtained from this is in terms of gram, as we are looking for the mass. Now, what will be the answer? Let us compute it into our calculator here. We have 24 times 1.93 times 1,000 over 2 times 96,500. The answer here becomes 0.24 gram. So the answer is the same as what you obtained in the first solving. So here conclude the mass of magnesium deposited at cathode was 0.24 gram. This is the answer for our question. This is the answer for this third example, and I hope the competence for you, I hope your competence is increasing now on the way to tackle different problems concerning with the Faraday's first law of electrolysis. Let us see a fourth example. It is stated that a steady current of 2 ampere is passed through a solution containing ions of metal M, and they are in M ions, for 9 minutes. The mass of metal M that is liberated is 0.3552 gram. Calculate the relative atomic mass of metal M, given that M is not the actual symbol of the metal, so it is just a representative of a certain metal. Okay, let us start. Let us write the solution here. Here, let us analyze the data given. We are given current, electric current. We are given current I. The electric current I is equal to 2 ampere. Also, we are given time t. The time t provided is equal to 9 minutes. Mean 9 minutes is equal to 9 times 60, so as to get seconds. So it will be 9 times 60, which is 540 seconds. So this is the time given. Another thing we are given, the mass of metal M liberated. Mass M liberated is equal to, the mass liberated is equal to 0.3552 gram. What is asked here? We are asked to find a relative atomic mass of metal M is equal to how much? Relative atomic mass of M is equal to how much? Now, let us choose the method we are going to use for solving this relative atomic mass from this data. Here, we are not given the electrochemical equivalent, and we don't know its relative atomic mass. So, directly here, the direct formula of Faraday's first law of electrolysis will not be applied, as we can't get the electrochemical equivalent. The only way we have here is to solve by first rebalancing the chemical equation for the reduction of M ions to form M as a metal. Now let us start looking at this equation. It will be at cathode, M ions will gain 2 electrons. We gain 2 electrons. 1 mole of M ion will gain 2 electrons to form M as a metal. M as a metal, as you see here. Now, what next? We can relate this balanced chemical equation by using concept of mole. By using mole concept and general idea of stoichiometry, that from the balanced chemical equation, 2 moles of electrons are equivalent to 1 mole of M. As you see, 2 moles of electrons are equivalent to 1 mole of M. Now, from there, we can change this number of electrons into Faradays and write these moles in terms of mass. You can express moles in terms of mass, and also these 2 moles of electrons in terms of Faradays. As you know, 1 Faraday is equivalent to 1 mole of electrons. So 2 moles of electrons, 2 moles of electrons are equivalent to 2 Faradays. Let us also rate the moles we have with the mass. How do they rate? Let us see. We say that number of moles is equal to mass over molar mass. Mass over molar mass. Now, here we have 1 mole of metal M. If we have 1 mole of metal M, this indicates that the mass and the molar mass are equal. If they are equal, it is where you can get the number of moles as 1. Now it means that if we let the mass, let the relative atomic mass of M be X. It means that if the relative atomic mass of M is X, for it to give us the 1 mole, it means that its mass is equal to relative atomic mass. Now here we say that 2 Faradays are equivalent to X gram of metal M. X gram of metal M, whereby this X is the relative atomic mass of metal M. As we have said that, for us to get 1 mole of metal M, it means that the mass of metal M is equal to its relative atomic mass. That is why I have put its relative atomic mass here, X. Now, this is according to the standard balanced chemical equation. Now let us relate it with the data which we have. But before we relate it with the data, which we have, let us convert this number of Faradays into Coulombs. Into charge. Here we are going to have 2 times 96,500 coulombs. As you know, 1 Faraday is equal to 96,500 coulombs. So here, instead of writing 2 Faradays, it is the same as the one who writes 2 times 96,500 coulombs. This will be equivalent to X gram of M. X gram of M. After that, you have to remember this X is the relative atomic mass of metal M. So you have to remember here we are going to relate this equation with the data given. The data we have current of 2 ampere and time of 540 seconds. So to relate these 2 values into coulombs, it means that we take current times time. So it will be on the left hand side. On the left hand side we have the charge in terms of coulombs. So here we are going to have 2 ampere times 540 seconds, so as to get the charge from the data of the question. Now this will be equivalent to the mass liberated. What mass of metal M was liberated? The mass liberated was 0.3552 gram. Now what next here is we have these values. We can solve the value of X. How do we do? We cross multiplication. We cross multiplication here. After crossing multiplication, we can be in the position of solving the relative atomic mass of metal M, which is given there as X. Now we are going to take 2 times 540 times X is equal to, as you see, 2 times 540 times X is equal to 2, this one, to 2 times 96,500 times this value of mass liberated, 0.3552. After there, let us compute by using a calculator. The values on the right hand side and left hand side. On left hand side, we have 2 times 540. We are going to get 1080. 1080 x times x times x. 1080 times x will be equal to, let us compute the data on the right hand side. We have 2 times 96 500,000 times 0.3552. Here we get 68. We get 68. Here we get 60. Here we get 68. 68 3.6. Now, after there, we get x by dividing by 1008 both sides. So we divide by 1008 both sides. 68 3.6. We divide by 1008 both sides by 1008 both sides. Now we are going to get our x will be equal to 68 3.6 over 1008. Now you have to know this one is going to give us, let us divide, it will be this one over 1080. So we're going to get 63.448. This is approximately to 63.5. This is the relative atomic mass of metal M. So according to this result, it shows that the relative, therefore, the relative atomic mass of metal M is 63.5. 63.5. And this is the solution for example 4. As I have told you before, that in this example we don't have an alternative because we were not given the relative atomic mass so as to calculate first the electrochemical equivalent. So the only approach to use for us to reach to the solution, for us to get this relative atomic mass, is only by balancing the chemical equation first for the reduction at cathode. After there, you can compute by using the idea of mole concept until the end. So after example 4, let us look example 5. Now let us look the fifth example. Fifth example has two parts, A and B. Part A states that what volume of oxygen measured at STP will be produced during electrolysis by a current of 5 ampere supplied for 30 minutes. Part B, which current will be able to produce 2 decimeter cubic of chlorine by electrolysis at STP within 1 hour. We are given that the molar mass, we are given that the relative atomic mass of hydrogen is 1, relative atomic mass of oxygen is 16, relative atomic mass of chlorine is 35.5, molar volume at STP is 22.4 decimeter cubic, and 1 Faraday is equal to 96,500 Coulomb. Now, let us start looking at the solution of this question by starting with part A. Now, let us start with part A. Solution for the question, part A. Part A, let us see the data given. Data given in example 5, part A, we are given electric current. We are given current electricity I. The current electricity given is 5 ampere. We are given is equal to 5 ampere. Also, we are given the time, 30 minutes. Time T is equal to 30 minutes. 30 minutes in 2 seconds will be equal to 30 times 60 seconds, which will be equal to 1800 seconds. So we have 1800 seconds. This is the time we have, but we are asked to use these two data to find the volume of oxygen at STP. The volume of oxygen at STP. Here, let us write the balanced chemical equation for this electrolysis. And as we are told that the oxygen gas was produced, it means that it was the electrolysis of hydroxide which takes place at anode. Now let us see the reaction at anode that involves the discharge of hydroxide to form water and oxygen gas. Let us see the reaction at anode. This reaction at anode involved the discharge. This reaction at anode involved the oxidation of hydroxide to form water and oxygen gas. As we are told that oxygen gas was one among the products produced. So let us see. It is hydroxyl ion. It was oxidized to form water and oxygen gas with 4 electrons. To mean that it lost 4 electrons to form water and oxygen gas. This is the balanced chemical equation. Now, from this is aqueous. From this balanced chemical equation, we can use the mole concept to relate the number of electrons, the number of moles of electrons, and the oxygen produced. As you can see, we have 4 moles of electrons. 4 moles of electrons is equivalent to 1 mole of oxygen gas. So we say that from the balanced chemical equation, 4 moles of electrons are equivalent to 1 mole of oxygen gas. Now, from there, we can relate number of moles and the number of Faradays. As we know, 1 mole is equivalent to 1 Faraday. Now, it will be 4 Faradays are equivalent to 1 mole. 1 mole of a gas at STP has 22.4 decimeter cubic. So here, as we have 1 mole, it means that it will be 4 Faradays will be equivalent to 22.2 dm cube of oxygen gas. Now, if it would be maybe 2 moles, we would take 2 times 22. It is 22.4. We would, if we do, it would be maybe 2 moles of oxygen gas. We would take to get the total volume. It would be 2 times 22.4. But as we are given only only 1 mole, we take that as it is 22.4 decimeter cubic. Now, let us change these Faradays into Coulombs, into charge, so as to compare it with the data we have. Here, we will have 4 times 96,500 Coulomb will be equivalent to 22.4 decimeter cubic of oxygen. As you can see, I have multiplied 4 times 96,500 Coulomb because 1 Faraday is equal to 96,500 Coulomb is equivalent to 22.4 decimeter cubic of oxygen gas. Now, if this is according to the balanced chemical equation. Now let's relate these values with the given values from the question. From the question, we have time of 1,800 seconds and current of 5 ampere. Now, when we take the product of these two, we get the charge, the total charge from the question. Now, the part of the charge is the left-hand side. So, to get that charge according to the current we have and the time we have, we take the product. So, it is current times time. It is 5 times 1,800. 800. These are coulombs. These are equivalent. These are equivalent to the expected amount of oxygen to be produced, which is in terms of volume, and it is what we are solving for. So we are looking for the volume of oxygen gas at STP, which will be produced when we apply the current of 5 ampere in 30 minutes. Now, let us see that value. Let us rate maybe the volume to be X. Let us rate the volume of oxygen gas which will be produced when we apply this amount of current within 30 minutes be X. Now, to get it, let us cross multiplication. We're going to cross multiplication. When we cross multiplication, to mean that this value will be multiplied by X and this value will be multiplied by 22.4. So what comes here, we're going to have 4 times 96,500 times X is equal to, will be equal to 5 times 1,800, 5 times 1,800 times 22.4 times 22.4. After there, let us multiply. Let us use a calculator to multiply the values on the left hand side and the right hand side. On the left hand side, you have 4 times 96,500. Yes, here we get 386,000 X will be equal to 5 times 1,800 times 22.4. Here we are going to have 201,600. 201,600, as you can see. Now, from there, to get X, we have to divide by 386,000 both sides. Now let us do it. We are going to have 386,000 X is equal to 201,600. So let us divide by 386,000 both sides, so as to get X. 386,000 both sides, so as to get X. Now X will be equal to 201,600 over 386,000. As these are equal, they cancel out, so we remain on the right hand side, we are remaining with the X only. Now let us see the value we get. That one over 386,000 we get is equal to 0.52. This is in terms of decimeter cubic. So we say now the volume of oxygen gas produced at STP will be 0.52 decimeter cubic. Now this is the solution for part A. For example 5, part A, this is the solution. The volume of oxygen gas that will be produced is equal to 0.52 decimeter cubic. Now, after the solution for part A, let us see the solution for part B. Part B, let us analyze data given for part B. Part B, as we see, we have the volume of chlorine produced. We have volume of chlorine produced is equal to the volume of chlorine produced, the volume V of chlorine. Let us say the volume of chlorine produced. The volume of chlorine produced is equal to, we are given it is 2 decimeter cubic. 2 decimeter cubic. This is the volume of chlorine produced. Also, what are we given? We're given also the time T. Time T is equal to 1 hour. To 1 hour, which is equal to 1 times 60 times 60 second. As you know, 1 hour is equal to 60 minutes. 60 minutes to change it into 2 seconds, we multiply again by 60. So 60 times 60, we get 3,000. We get 3,600 seconds. Now this is the time given, 3,600 seconds. Another data required here is current electricity, and in this question we are asked to calculate the current electricity required. So current electricity I is required. This is the required value. So we are required to calculate the amount of electric current required for this electrolysis to take place. Now here, the same, we are going to use a balanced chemical equation, and you see it is the electrolysis of chlorine. If it is the electrolysis of chloride ion to produce chlorine gas, it means that it is an oxidation reaction which takes place at anode. So here let us see the reaction at anode. Reaction at anode. Reaction at anode. As usual at anode, chloride ion is going to be oxidized to form chlorine gas. Now, chloride ion is going to be oxidized to form chlorine gas. As you see, chlorine gas, as you see, 2 ions will require 2 electrons. Here, after that, we are going to use this balanced chemical equation and to relate with the mole concept. Now, we are going to relate the number of moles of electrons required and the number of moles of chlorine gas produced. Now, from this equation, it shows that 2 moles of electrons are equivalent to 1 mole of chlorine gas. 1 mole of chlorine gas, as you see. If so, let us convert directly this number of moles of electrons to Faradays. 1 Faraday is equal to 1 mole of electrons. So these 2 moles of electrons will be equal to 2 Faradays. Now 2 Faradays will be equivalent to 1 mole of chlorine gas. When we change 1 mole of chlorine gas at STP, it will be equal to 22.4 decimeter cubic of chlorine gas. Now, here, let us convert Faradays into coulombs, to charge. It will be 2 times 96,500 coulombs. Coulombs will be equivalent to 22.4 decimeter cubic of chlorine gas. I have multiplied 2 by 96,500 to get the total amount of charge, because 1 Faradays is equal to 96,500 coulombs. Now, after that, these are the value from the standard balanced chemical equation. Now let relate them with the values from the given equation. From the given equation, we are given 1 hour, which is equal to 3,600 seconds. Also, we are given the volume produced, the volume of chlorine gas produced is 2 decimeter cubic. Now it means that on the part of volume here, 2 decimeter cubic of chlorine gas are equivalent to the amount of electric current produced times its time to get the charge. So the amount of current is not known. It is what we are looking for. I times time is 3,600 seconds. So here we will be in the position of being capable to find the value of I, which is the current. To get it, let us cross multiplication. When you cross multiplication, we take I times 300, we take I times 3,600 seconds times 22.4 decimeter cubic will be equal to 2 times 96,500, 2 times 2, this 2 times 2 times 96,500 coulombs. Now here, let us multiply Let us take the values on left hand side and right hand side. On left hand side we have 3600 times 22.4. Here we get 80,640 times I is equal to 2. On the right hand side we have 2 times 2 times 96,500. So here we get 386,000. Now, what next is to divide by 80,600 both sides, is to divide by 80,640 both sides so as to get I. Now here we have 80,640 I is equal to 886,000. We divide by 8,640. 8,640 both sides. Here we are remaining with the I. I will be equal to, when we divide this value, we get over 8,640. We get 4.78. 4.7867, which is approximately, is this ampere, which is approximately to 4.8 ampere. This will be the current. This will be the current. Now we say the current, the amount of current electricity, the amount of current electricity, to be applied, to be used, will be 4.8 ampere. 4.8 ampere. And this is the answer. This is the answer for this, for example 5, part B. For example 5, part B. Example 5, part B, the answer is 4.8 ampere. Now, this is the end of my presentation on the Faraday's Festival of Electrolysis. I hope you have understood well because I have used many examples. Via all 5 examples, I am sure that you have understood well. Thank you for attending this session. Have a nice moment. Bye.